Okay, welcome. This is Dr. Morton, and this is the video lecture for Wednesday, the last day of August, August 31st. And so what we're going to do, I want to cover a little bit about how we get the min term and max term expressions out of a truth table. Now remember, we have two canonical forms, the SOP and the POS, and we're going to cover these fairly extensively in Chapter 5, but I do want to introduce them here just so you're kind of aware of them, and then we're going to come back and really pound them home in Chapter 5. Okay, so we can take any truth table and we can generate a SOP form which has some input AND gates and one output OR gate. And we call the input AND gate terms, we call min terms. And the output OR gate is our final output. And that generates all the values for F. We do the same with the POS form where we have a set of input OR gates and one output AND gate. So let me first just touch on the syllabus, and then we'll get right into it. Okay, here's the syllabus, and what I want you to see is that the here we are on August 31st, and so we're still on Chapter 2, so we're kind of ahead in the lectures, and that's okay. I will talk, I'm going to try and finish a little bit early, and I'll talk a little bit about homework 2, which is due tonight in just a couple of hours, and if you're struggling with it, then I'll give you a little help. But I think it's pretty straightforward, so we will do that, and I'm going to save some time, and I'm going to try and do this all in about 35 minutes or so. Okay, so that's the syllabus. We'll move on from there. Okay, so here's the book, and like I say, we're going to cover Chapter 4 in a minute. But first, before we come back to this, I want to introduce some of the stuff you're going to see in Chapter 4. So just kind of hold your appetite for Chapter 5. Hold your appetite for Chapter 4 until I give you a little intro for Chapter 5, and then we'll come back to Chapter 4. Okay, hopefully that wasn't too confusing. All right, so what I want to do, I want to talk just a little bit about how we take a truth table and turn it into the SOP and POS forms. So if we look at a truth table, let's take a 3-variable truth table. So remember, a truth table has independent variables, in this case A, B, and C. And if there are n independent variables, we're going to have 2 to the n rows. 3 variables, so 2 cubed is 8. So we're going to have 8 rows, and then we're going to have an output function F. We could have more output functions. We could put F0, F1, F2. Whenever we add an additional variable, we double the number of rows in our truth table. Whenever we add another function, we just add another column. So this could be F0 and this could be F1. But we're going to focus on just a single output function right now. Okay, so we know that our 8 rows our higher order variable is going to be 0 for 4 rows and then 1 for 4 rows. We'll bring this on down, and then we'll put this bottom line in, and then we know that our next hierarchical variable is going to be 2 zeros, 2 ones, 2 zeros, and 2 ones. And then finally our lower order variable is going to flip each row, 0, 1, 0, 1, all the way to the 8th row. All right, now I'm just going to pick some variables here. I'll do 1, 1, 1, and I'm going to put zeros where we don't have them, and then a 0 here, and then a 0 here, and a 0, and a 1. So it turns out we have 1, 2, 3, 4. We've got 4 ones and 4 zeros. Now, that's just an accident. We could have 5 ones and 3 zeros. We could have 7 ones and 1 zero. If we have all ones or all zeros, it's kind of a simple case, and we don't really worry about that. We wouldn't really expect to have that, but it certainly can arise when we start doing our state machines. It comes up all the time because of don't cares and whatnot. We'll talk about that later. Now, if for some reason one of these rows, and where do we get the F from? We get it from our customer, or we get it from God. If one of these rows is known to the customer to never occur, so it'll never be the case, say, that A is 1 and B and C are both 0. In that case, instead of putting a 1 here, we'll put an X to tell us that we can choose that to be a 1 or a 0, whichever is more convenient for simplifying our function. Now, we haven't done any simplifying yet. We'll get into that. And we can simplify this with switching algebra, which we're going to get into in chapter 4 here, or we can simplify it with the K-map, but we're not going to do that. Now, what I want you to see is, and we're going to cover this extensively in chapter 5, so don't worry if it's a little fuzzy when we're through here. The first thing I want you to realize is that every row has a minterm associated with it, and every row has a max term. Now, we don't normally write these out, but I'm going to do that just to make it a little more obvious. And what's also true is that the solution we get with the minterms is going to be exactly equal to the solution we get with the max terms, but they'll just be in different forms. The minterm solution will be in SOP form, the max term will be in POS form. And every row has an associated minterm. But the way we actually get our minterm expression is we OR together all the minterms associated with rows that the desired output for F is a 1. So we're gonna and we number these minterms. This is minterm 0, 1, 2, 3, 4, 5, 6, and 7. Remember, we always start counting with 0 in logic design, unless we don't. All right, so our minterm expression, and I'm going to write a few, and then hopefully you'll see the pattern, and it's super easy, but totally confusing until you see the pattern. All right, so all the minterms are going to be essentially representations of an AND gate, 3-input AND gate. So this is going to be A prime, B prime, C prime. That's the minterm for row 0. For the row 1, it's going to be A prime, B prime, C. And that's because instead of a 0 on this term, C is a 1. But A and B are still 0. So they're A prime, B prime, which means they're zeros, and C is a 1. And then here we have A prime, B, C prime. Because now C is back to a 0, but B is a 1. And then finally we have A prime, B, C. And then we have A, B prime, C prime, where A is a 1 and B and C are 0. And then we have A, B prime, C. And then we have A, B, C prime. And finally, A, B, C. Now the max terms these are going to be AND terms, or we'll call those product terms. Product terms. The max terms are going to be OR gates, or we'll call them sum terms. Sum terms. And the max terms are going to look a little different. We're going to be ORing things together, so we're going to use plus signs. And we also, instead of primes, we're going to flip that around. It's actually the exact inverse of each of the minterms. But remember, the max term solution and the minterm solutions are equal, not inverses, because we only use the max terms from the rows where the desired output is 0, and we only use the minterms from the rows where the desired output is 1. So basically, we never use a minterm and a max term from the same row for our POS and SOP solutions. Okay, so here are max terms. This is going to be A plus B plus C, and we'll put this in parentheses to make it easier to see it's an OR gate. We could also put these in parentheses, but I'm just going to do the first one because it gets cluttered. And then the next one would be A plus B plus C prime. And the next one's going to be A plus B prime plus C. And then A plus B prime plus C prime. Now you begin to see the pattern. And finally, so then it's going to be A prime plus B plus C. And then it's going to be A prime plus B plus C prime. And then finally, A prime plus B prime plus C. And then finally, A prime plus B prime plus C prime. Now notice, these are ORed together, these are ANDed together. These are all, each of these terms are the inverse of the other. And this is why our POS solution has OR gates as its inputs and one output AND gate, and our SOP solution has AND gates as our input and one output OR gate. So the SOP stands for sum of products. So we're going to OR together our product terms. Now this is, again, maximal confusion for students because the input layer, we're calling it the product terms, which is the last thing in our SOP abbreviation, but it's really the first layer. So that's confusing. It's kind of maximally confusing. And also, the min terms, we use the ones, and the max terms, we use the 0. You would think the max terms would use the ones, and the min terms would use the zeros. But it's exactly backwards. So all of this nomenclature is designed to confuse students. Now, in our particular case, let's write the min term expression. So f equals, and we're just gonna OR these things together. So we take the ones where it's 1. So we're going to use min term 0, 1, 4, and 7. Sometimes we'll write that the sum of the min terms 0, 1, 4, 7. And then let's just write that out in the, we call this the shorthand notation. These are the 4 min terms we have to, because that's the 4 ones that show up on our truth table. And now, and again, where did we get this F from? We got it from God. We were given it. It came from our customer, and our customer is God, because if we don't have customers, then we go out of business. All right, so let's write the expression. So we're going to take the first 2 min terms for 0 and 1. So it's going to be A prime, B prime, C prime, plus A prime, B prime, C, plus, then we're going to take min term 4. So that's down here, A, B prime, C prime, because it's also a 1. A, B prime, C prime. And finally, we're going to take min term 7, ABC. Now this is our min term expression unsimplified for F. Now we can usually use some of our switching algebra, which we're going to cover in chapter 4 in just a minute, and we can simplify it. Or later on when we get to chapter 6 or 5 or whatever it is, 6 I guess, or 7, we're going to do K-maps. Okay, but that's going to be after the first test, so don't think about that yet. And K-maps are going to be a lot easier than switching algebra, so you'll struggle a little bit in this first part with the switching algebra, but then things will get really easy with K-maps. All right, so there's our function. And remember, we have the sum of the little m's, 0, 1, 4, 7. All right, our max term solution, so this is SOP, and then the POS solution, you probably can't see it here, POS, for F, it's going to be exactly equal to the SOP, just a different form. And we write this, the product of the big M's. And now, what do we have? Well, the zeros are 2, 3, 5, and 6. 2, 3, 5, 6. And that's just going to be equal to, so min term 2 is going to be A plus B prime plus C. But we have to put these in parentheses. So A plus B prime plus C, quantity times 3, which is A, B prime plus C prime, A plus B prime plus C prime, quantity times, and then 5 and 6, so what is 5 here, I guess? And that's going to be A prime, B, A prime plus B plus C prime. So A prime plus B plus C prime, quantity, and finally times 6, A prime plus B prime plus C. All right, and we're going to hopefully simplify this also. And these two expressions, this one, which has and terms ORed together, and this one, which has OR terms ANDed together, because remember there's implied multiplication or ANDing between all these quantities, they're exactly equal. Okay, that's what I wanted to show you. Armed with this, let's look at chapter 4. Sorry. Okay, there we go. All right. So, and let me put this down for a minute. So remember, we have this picture. We kind of have an idea. Our idea basically leads us to some truth tables, and then boom, we get a device. All right. So now we're going to talk about how we do this switching algebra part. And okay, so the first thing I want you to do is the learning objectives. We're going to cover all the theorems. You should be able to write the 3 conversion theorems, the 3 simplification theorems. There are actually 4, but we're going to leave one until we get to K-maps, called the consensus theorem. We'll mention it, but we're not going to really study it until we get to K-maps. And then you should be able to simplify a logic expression using our simplification theorems. And you should be able to switch from SOP to POS, or the AND-OR form to the OR-AND form, also using our conversion theorems. So simplification theorems and conversion theorems. And we use both of them to do the conversions. And then we're also going to show you how to invert with De Morgan's laws. I may not get to that today. I just want to get this started. Remember, every chapter has got a video. You should watch this video, and it's going to cover the whole chapter. And then finally, here are the theorems. Okay, so we have the trivial laws. I'll just mention these briefly. So we have operations with the constant 0 and 1. I think I've talked about this already, but x ORed with 0 is x ORed with 1 is 1. X ANDed with 1 is x, and x ANDed with 0 is always 0. And if you think about that for a minute, it's obvious. Remember, AND gates, all the inputs have to be 1. So if one of them's a 0, it doesn't matter what the others are, it's a 0 out. And then in the OR gates, if any input's a 1, it's a 1. So here you have a 1, so it doesn't matter about x here. Here, it just depends on x. Here, you have the other inputs a 1, so it just depends on x. All right. And then we call this the idempotent. And that's x ORed with itself is x. X ANDed with itself is x. So if x is 1, it's going to be 1. And if x is 0, it's going to be 0, obviously. And then it doesn't matter the order. X ORed with y is the same as y ORed with x, and vice versa for ANDing, or same for ANDing. And then the complements, x ORed with its complement is always 1. X ANDed with its complement is always 0, because here in this AND situation, one of them's 0, and here one of them's 1. So you always get a 1 out for the OR gate, and you always get a 0 out for the AND gate. And then it doesn't matter the order in which you group them, you get the same thing. Now this is only true for the AND and OR gates. For the NANDs and NORs, it's not. We'll show you why. It's because of the inversion. And then here we have the double inverse. If you inverse something twice, you get back to the beginning. Okay. Now, these are the more important ones. The simplification laws, where we combine terms. Now, this is really important. If you have xy plus xy prime, you can drop the y because it changes, and everything else stays the same. You could do the same thing with with wxy and wxy prime. You would still drop the y, and you'd wind up with wx. So in this case, we can combine these terms and drop one of the variables, giving us a single variable in this case. Here, same thing. This is just the OR form, the POS form essentially, and you can combine these because the y changes, and you just wind up with x. Here we can eliminate a literal. This one's a little harder to see. X plus x prime y equals x plus y. I'll prove it later when we'll go back and work on this some. I just want to expose you to it today. And then x y prime, x times the quantity x prime plus y. The x prime here is useless. This just gives us xy. And if you think about it, if you multiply the x in here, x times x prime is always 0 plus xy. So that's just xy. And here, if the x is 1, then it's just 1. Then x prime would be 0. That term goes away anyway. And if x is 0, it only depends on this term, which depends on y then, because x prime would be 1. So that's just x plus y. All right, eliminate a term. If you have xy plus x, you don't need the xy term. All right, you just need the x term. It's a little confusing when you compare this to this, but it should make sense to you. All right, and then here we have the quantity x plus y times x, and that just equals x. The y drops out. The difference here is there's an x prime in the parentheses, and here there's an x prime times y, added with y. Here it's just x. So that's why that's different. Okay, and we're going to use these three theorems extensively. This is the consensus theorem. The point is that x plus y plus x prime z, this yz term is superfluous. You don't really need it. But it's also a legitimate term. So you can add it or you can get rid of it depending on what helps you. And the same over here. This yz term is superfluous. And with a K-map, it's easy to see. Without a K-map, they're tricky to see. All right, those are our three simplification theorems, plus the fourth one that we're going to leave alone for a while. And here are conversion laws. There are really three of them, two on this line and this multiplying and factoring in basically two different forms, but it's the same thing. The first distributive law is just like algebra. You multiply the x into the quantity, and you get x times the quantity y plus z. You get xy plus xz. Again, remember, this is ANDing and ORing, not multiplication and addition. The second distributive law, which we call C2, is just x plus yz equals x plus y quantity times x plus z quantity. Now notice this is not legal in switching algebra. This is not legal in regular algebra, but it is absolutely legal in switching algebra. And we even have a little corollary down here, which is x plus abc is just x plus a quantity times x plus b times quantity x plus c. Keep this in mind. This may very well show up on a test. All right? It's the same idea. You could use this first distributive law and just apply it a couple of times. You'd get the same thing, or 3 times, I guess. Okay. And finally, the multiplying and factoring. So sometimes I'll refer to this as C3. Sometimes I'll call it M and F. I'll usually call this C1 and this C2. Or first distributive law, second distributive law. All right, multiplying and factoring, C3, xy plus x prime. Notice there's an x here and an x prime there. And what we get then is we switch these around. I'll show you a little trick here. So let me transition this. Okay, so if you look at this, that one's really, if we have x, y plus x prime z. All right, we draw these little lines in this little box, and we do that to keep them straight. So what we wind up with is x plus z quantity times x prime plus y. And the lines kind of help us. The x prime is connected to y, the x is connected to the z. Okay? So that's how we use that. And it's the same way here. We take the x and we connect it to the y, and here we take the x prime and connect it to the z, and we go back this direction. And it doesn't matter, we could just as easily write this x prime y plus xz, and we just have to keep it straight. Then we'd wind up with the x prime times the z and the x times the y. All right, and we use these little brackets to help us keep this straight. All right. Now, that covers all the laws except for this De Morgan's laws. And basically, De Morgan's laws, we want to do the inverse. So if we want to inverse x, y, z, then we just wind up with x prime plus y prime plus z prime. We invert the operators, which in this case are ands, and we convert those to ors, the pluses, and we prime all the variables. Now the dual, which isn't used much anymore, we use it to generate these dual column here, but we invert the operators, but we don't prime the variables, and that's the dual. This used to be when we would combine positive and negative logic code. We'd take the dual of the negative logic code, and then we could use it with the positive logic code. And the same in the opposite here. X plus y plus z prime. If you invert that quantity, you wind with an and, because you invert the pluses to times, and you prime all the variables, so you get x prime, y prime, z prime, all anded together here, x, y, z ORed together, and so forth. The dual is the same, except you didn't prime the variables. So you just go from the OR gate to the AND gate, essentially. All right, we're going to come back. We're going to do this a bunch, and I think this is going to make a lot of sense to you. Okay, now let's see. Okay, so now we have, I'm just going to go through some of the slides here, and then I'm going to shift to the homework here in just a few minutes. Let's see, we're 23 minutes in or so that's no big deal. Okay, all right, so we went over the learning objectives already, so I'm not going to repeat those. So the main thing here, one of the problems with switching algebra is that you're always tempted to think about it as regular algebra, and it's not. So you've got to kind of get that out of your head right off the bat. Our variables are limited to just 2 values, 0 and 1, and that changes everything. It also makes it easy to prove stuff, because you can show that for all possible values of all your variables, that the two sides are exactly equal. Since your variables, say if you have 3 variables, the only possible combinations, there are only 8 possible combinations of all the variables. So if you show for all 8 possible combinations, both sides work out to the same thing, then you've proven that theorem. And you can do that with basically a truth table, and you just make the output functions different parts of the sides and build them up until you get your final 2 columns or the 2 different sides, and you show that for every possible combination they result to the same output. Maybe I'll do one of those in a minute. Yeah, let's do one now. So let's see. Okay, so let's take the second distributive law, and we'll go through that right now. That's a good idea. We'll just do that. Okay, so here's the second distributive law: x plus yz equals quantity x plus y, quantity x plus z. Now you know that that's not legal. You can't do that in normal algebra. Okay, but you can in switching algebra. So let's just show how we can do this. Well, so one way is to look at all possible values of x and y and z and show that the two sides are equal. So if we create a truth table with x, y, and z, and then we have some columns over here. So we'll do 1, 2, 3, 4 rows where x is 1, and 4 rows where x is, x is 0, and 4 rows where it's 1. And then 0, 0, 1, 1, 0, 0, 1, 1, and finally 0, 1, 0, 1, 0, 1, 0, 1. All right, and then our first column we'll say so we have a column that's just x right here, so that's easy. Let's do a yz column. Y ANDed with z. We'll put a little dot in there. Okay, so if we AND y and z, 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0, because remember, both inputs have to be 1. 1 ANDed with 1 is a 1. 0, 0 is a 0. 0, 1 is a 0. 1, 0 is a 0. And 1, 1 is a 1. So that's what we get for the yz term. And then, so if we just have the x term, I'll put it in here. It's basically 1, 2, 3, 4. 1, 2, 3, 4. And then we're gonna OR those together. So basically, so this side then, this x plus yz is just ORing these. So here we go. 0 OR with 0 is 0. 0 OR with 0 is 0. 0 OR with 0 is 0. 1 OR with 0 is 0. 0 OR with 1 is 0. 0 OR with 1 is 0. 0 ORed with 1 is, oh, I'm sorry, I screwed that up. 1 ORed with 0 is 1. It's an OR function, not an AND function. And then these are all 1. And finally, 1 ORed with 1 is 1. Okay, so we have 3 zeros and the rest are 1s. All right, now we're going to do, these two. We're going to do this, then we'll do this, and then we'll do the result ORed together. Okay, so let's first do x or y. So x or y. So all we do is look for a 1. So these are 0, but y is a 1, y is a 1, x is a 1, x is a 1, x is a 1, x is a 1. So we have 2 zeros, and then we have 1, 2, 3, 4, 5, 6, and then we'll do the other one. Let's do x plus z. So now we have 0, 0, 0, 1. So we have 0, 1. And then we have 0, 0, so that's a 0. And then we have 0, 1, so that's a 1. And then we have 1, 1, 1, 1. 1, 2, 3, 4. And then if we do the column where we AND these two columns, x plus y quantity ANDed with x plus z. So we're going to AND these two columns. So 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 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 And 1 ANDed with 1 is 1. And notice, this is our x plus y quantity times x plus z. And we're comparing this column to this column. And they have to match if it's true. 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. 0, 0, 0, 1, 1, 1, 1, 1. They're exactly equal. So that proves this expression. Okay? So that's one way you can prove it. And I'm not going to do any others because they get kind of boring. But I want you to be able to do that. Okay, so notice here that we have, so keep in mind it's not regular algebra, that our symbols, our variables, are really not 1s and 0s. They're true and false. And we don't really have addition and multiplication because there's no such thing as division or subtraction. We only have ANDing and ORing in this case. And also the variables that are inverse, essentially. Everything can be proved or disproved. Nothing is left unresolved. We don't have any situations where we can't figure out the answer. We can always figure out the answer. And often there are multiple equivalent but different solutions for the same thing. When you're doing switching algebra, I want you to write the expression you're using and put an arrow to show how you're applying it, because you can apply them in both directions. So remember, when we go back to, when we look at this table, which we're getting to, so we already looked at the trivial laws, we looked at the simplifications. So basically, the trivial laws, the simplifications, the conversion laws, and the De Morgan's laws, that's it. That's all you can do. Those are the only legal things you can do in switching algebra. But that allows you to really manipulate logic expressions tremendously. Okay, and I think, and so here's kind of the final thing. All right. All right. Well, I had already done this, so I guess I didn't have to draw it out. But anyway, same thing. Okay. Here's the proof of the multiplying and factoring using a truth table as well. These two columns match, so it proves it. What this two green columns shows is that for all possible values of x, y, and z, both sides of the multiplying and factoring theorem always resolve to the same thing. They're equal. So it's proved. Now, if these could take on an infinite number of values, then that would not be possible. But in switching algebra, they can only be 0 or 1. Only 8 combinations of our 3 variables possible. Okay. Okay, let me just talk a little bit about our POS and SOP canonical forms. So we've introduced these. We're going to really work a little more on them in the next chapter, but I want you to see the logic expression. Again, remember that there are 2 canonical forms, SOP and POS. Stands for sum of products. It means we're going to OR together a bunch of input product terms. The OR is our output layer, the last layer. The product terms, the AND terms, are the input layer. And same here at CCAVIT. We're going to AND together a bunch of input OR terms or sum terms. So every truth table can be represented in an SOP form and the POS form, and they should be exactly equal to each other. Now, they oftentimes will look at both possible outcomes and we'll pick the simplest if we're using this form. If we're going to convert it to NAND gates, which are easier to synthesize than AND and ORs, we'll use the SOP form. If we're going to convert it to hardware that's made up of NOR gates, a NOR input layer and one NOR output, we're going to use the POS form, because we can go from POS to NOR really easily. We can go from SOP to NAND real easily. But you can't go from SOP to NOR. You have to first go from SOP to POS and then to NOR. All right. Yes. And we can always represent our logic functions in 2-layer nets. Turns out in many designs we have multiple layers, but that's for a bunch of other reasons. But because we have steps and processes and state machines and other stuff. But you can reduce them to 2 layers, and occasionally we'll expand it to 3 layers because sometimes we'll save gates, but at the cost of more propagation delays through an extra layer. All right. And you can always have a degenerative term that's just a single variable, which means, like in this example here, you can see we have these gates here. We could have a single term which wouldn't need an actual gate, and it can just go to the output gate directly. When we convert to NAND, though, we have to invert it because it becomes a little weird. All right. Notice that the SOP form and the POS form are different forms, but they're always equal to each other. All right, let me do one thing here, and then I'm going to go look at the homework for tonight, which you have just a little bit of time left to do. Okay, so we're going to factor this to get 4 product terms. So it's I'm going to write it down, and then we're going to work on the paper over here. I meant to pause the video when I sneezed, but I missed it because I had to sneeze so bad. So sorry for the sneeze. All right. Okay. Here we go. So here's, I'm going to write it down and then I'll switch to the camera. ACD plus B prime. A prime, B prime,
I didn't get that.
D.
Could you try again?
My gosh. Siri woke up when I sneezed. Plus, so A prime, B prime, D, plus A prime, B, C, plus A, C prime, D prime. Okay, so I'm going to switch over here, or maybe I'll do it on this to save time, and then I'll get to the homework. Yeah, I'll just do it here. All right, so the first thing we do is we use the first distributive law, C1, conversion theorem 1. And we're going to factor out A from two terms and A prime from two terms. So we look at this, we notice we have an A in every term. We don't have a B in every term. We don't have a C in every term. We don't have a D in every term. But we can arrange our terms so we have ACD and AC prime D prime and factor out an A. And we can arrange it so we have the other two are A prime B prime D and A prime B C, and we can factor out an A prime. So then it looks like this: A times CD plus C prime D prime plus A prime times B prime D plus BC. All right, so that's great. That's easy. Now we can use the multiplying and factoring theorem, because we have A times something and A prime times something. So we can apply it. We can actually apply it two times inside the parentheses, because we have CD and C prime D prime. So we can pick either C or D. In this case, I guess I picked C. So we'll pair C up with D prime and C prime up with D, and we'll get C prime plus D prime quantity times C prime plus D quantity. And we'll do the same inside here. Okay, so we'll do that. So that'll give us A times these two things and A prime times these two things using the B and the B prime. Now we'll apply the M&F theorem one more time with an A and an A prime. We'll take the A and we'll basically we have an A times something and an A prime times something. So we're going to wind up with A plus this something and A prime plus this something. Those quantities times each other. And so that'll give us this. A prime plus this over here, or this here. So we take the A prime times the quantity C plus D prime times the quantity C prime plus D. And then we'll multiply that whole thing times this whole thing, which is A plus all this. And so now the next thing you should notice is what's in here is very much like x plus yz, where A prime would be x and C D prime would be y, and the quantity C prime plus D would be z. So now we take x plus yz, the second distributive law, and that's going to convert to x plus y quantity times x plus z. So we're going to use the second distributive law on this part and on this part, and what we get is that A plus B prime plus C quantity times A plus B plus D quantity times A prime plus C plus D prime times quantity A prime plus C prime plus D. Now that's an example, and we're going to do more of these, and we're going to make you able to do these with some work and effort, but I don't expect you to turn into a switching algebra maven or anything. Just so you got some level of confidence to do the fairly straightforward. This I would consider as a hard problem, and I'm going to give you easier problems on the test. Okay, and one of the things we also do, we always look to see if we can use any of the three simplification theorems first before we wade into this. In this particular case, we couldn't. But if we can, we do. All right. Let me look at the homework real quick, and we'll be done. Okay. So now we have, here's the web page. We scroll down to the homework right here. And we open that file. And here it is. We'll blow it up a little bit so we can just see the one page. All right. So here's some of the problems, and let's see, I think we're turning in chapter 2 tonight. So to convert from one non-decimal base to another non-decimal base, we have to first go through base A to decimal, and then from base B to decimal, unless A and B bases have a perfect relationship like binary and hex. All right. So in this case, we had 14.323 base 5 to base 9. Okay, the first thing is you have to do this by first converting 14 to base 10, and then 14.23 to base 10, and then you take the integer portion of that and convert that integer portion to base 9, and you take the fractional portion and you convert that to base 9. You have to do all your math in base 10, so you must go through base 10, because that way you can do all the math in base 10. All right, let me work on that one. Let's talk about the other ones first, and I'll come back, because that's going to take a little bit. What happens when you take the 2's complement of binary 0, 8-bit 0? What happens is you get 0 again with a carry out of a 1, but in 2's complement math, we ignore the carry out. First write minus 128 as a 2's complement 8 bits, then take the 2's complement of that. And what do you get? I'm not going to tell you the answer, but remember, when you have a 2's complement value, you can fit, so in 8 bits, we can fit 512 things in, 0 through 511. No, I'm sorry, it's just a lie. We can fit 256 things in, 0 through 255. But when you do 2's complement, you cut that in half, you get half the negative numbers and half of the numbers, half positive numbers. So half of 256 is 128. So we have 128 negative numbers, but remember we start with 2 to the minus 1. And so we basically have minus 1, sorry, we start with minus 1. So we go through minus 1 to minus 128. But on the positive side, we go from 0, which is a positive number, to plus 127. So obviously, in 8 bits, we can't fit positive 128 because we've used up our 128 positive numbers, and we only got the 127 because we had to start with 0. And we get one more when we go negative because we start with minus 1 and not 0. There is no minus 0. Okay, so it turns out when you do that, I'm going to let you do that, but don't be surprised about what you get. You should be able to think about it and see, yeah, you're not going to get plus 128. So what are you going to get? All right, and then write a little sentence or two that explains why all math operations are addition. And finally, yeah, so I kind of answered this already. When we write a binary number in 2's complement forward for any specific number of bits, say like 4 bits, we can represent the same number of positive and negative numbers. Why is that true? Well, in 4 bits you get 0, 1, 2, 3, 4, 5, 6, 7. So that's 8 values. And you get minus 1, minus 2, minus 3, minus 4, minus 5, 6, 7, and 8. So you get 8 negative numbers and 8 positive numbers, but you start with 0 on the positive side. And that's why they're the same. I pretty much answered that, but you have to write that out. Okay, let me switch to the paper, and I'm going to do this base 9 thing, and then we're going to wrap it up, I hope. Actually, we'll be done. Okay, so the number was 14.23. Let's see, let me get one more. Let me get one more piece of paper. Okay, so here we are. Okay, so the first thing we're going to do is 14.23 base, what did I say, base 5. All right, and remember, what are the symbols we have in base 5? 0, 1, 2, 3, and 4. We can't have 5. We have 5 numbers, but we start with 0, so we get 0, 1, 2, 3, 4. And in base 9, we get 0, 1, 2, 3, 4, 5, 6, 7, 8, but we don't get 9 because we only have 8 numbers, not 9. And we only have 9 numbers, not 10, in base 9. Okay, so first thing we're going to do is do this conversion. So remember, the 4 is just 5 to the 0 multiplied by 5 to the 0, and the 1 is just multiplied by 5 to the 1. 5 to the 0 is a 1, so that's just going to be 1 times 5, or 5, plus 4 times 1, or 4, plus 2 times 5 to the minus 1, or 1/5, and 3 plus 3 times 1, 5 to the second, or 1/25. All right. So, okay. So now I have 2/5 plus 3 25ths, and so if I multiply this by 5, I get that's going to equal 13 25ths. All right, so let's do that division on the calculator, and I'll pause it. It turns out that equals 10.52. So our first conversion then is going to be 5 plus 4 plus 0.52 in base 10. So that's going to be 9.52 in base 10. Now we're going to go to base 9. So we have to do two different things. We have to treat the integer portion differently than the fractional portion. For the integer portion, I'm just going to take 9 and I'm going to divide it by 9. Works out nice. That's 1, remainder 0. And we're going to divide 1 by 9. That works out to be 0, remainder 1. So in base 9, 9 is actually 10. Base 9. And now we have to do the fractional portion. Well, to do that, we just take the fractional portion and multiply by the base. So 0.52 times 9. All right? And that equals 9 times 2 is 18, carry 1. 9 times 5 is 45, and 1 is 46. 4.68. We take this 4 and we add it to our 10. And so, here, let me write this down here. 10 point, so that's 4. And then we work on the 6.8. Now I'll write the 0.68 up here, and we're going to multiply that by 9, and we'll get our next digit. And that equals 6.12. So we put our 6 down here, we get rid of that, we multiply this by 9. 9 times 2 is 18, 9 times 1 is 9, and 1 is 10. We put a 1. And we can keep going, and eventually we'll just have more and more digits, and eventually you'll start to see a repeat pattern. I don't know if it terminates, it probably doesn't, so it'll probably just keep going. It might terminate, I don't know, I didn't do it. But when you finally start to see a repeating pattern, then you can quit. And so this is base 9. So our final answer is 14.23 base 5 converts to 10.461 base 9. Now that's not really 10, that is actually 9. But we write 10 in base 9 to equal 9. Makes sense. Okay, so that's the conversion. And we had to go through decimal to do this because I can't do math in base 5. I can't do math in base 9. You have to memorize all those multiplication facts and the division facts and a whole bunch of stuff, and you just how to borrow, and it gets very confusing. You just don't know how to do it, and you don't know the facts, and so it would be real awkward. So you have to go through decimal in order to make this work. And of course the decimal over here, what was my decimal? It was 9.52 base 10. And notice that our numbers in lower bases are always bigger. So this is base 10, a bigger base. It's going to look smaller than the other bases. So 10 in base 9, 14 in base 5. All right. I think with that I'm going to quit, and I'll do another video for Friday, and I'll post it hopefully by late Friday night.